那我们开始吧。
Okay. Welcome everyone. Thank you for coming to the Sensor Talk. My name is Yipan. I'm a staff engineer in LinkedIn, working in the Sensor team. As title said, right? What's Sensor? Sensor is a stream processing platform. Today we're going to dive deep into it. Okay, this is the overview of my talk. So first, we'll briefly talk about what is the stream processing. What does this mean? Is it buzzword or is it real mean something? And then there are a few basic concepts that we'll have to go through before we dive into the sensor architecture. Then I will talk about how we run sensor on top of YUM, and how we use sensor to do the stateful processing, and then a brief introduction of the upcoming features in sensor. So stream processing, what does it mean? The main thing is the response latency in reacting to the real data. So there's a full spectrum of latencies here. One, you can use the RPC mode, which is purely synchronized. You provide the data, you make a call, you get results immediately within milliseconds or a few milliseconds. And there's another end of the spectrum, which is the Hadoop and offline processing. Then you have a large scale of data, you do the batch process, but the latency is probably in hours or days. So this is what exists in maybe like 5 years ago. And then recently more and more internet scale companies start to realize, or even not internet, like the financial or even the health insurance, those companies start to realize, okay, batch is nice because it allows you to scale out and do a lot of data crunching on top of the big data, but it's too slow. What people want is a shorter latency processing on top of a large amount of data. So that's where the stream processing comes in. That basically we need a certain solution that in this spectrum that provides a real-time or near-line processing engine for the big data crunching. So that's where Sensor comes in. Typically, our Sensor platform provides milliseconds to minutes of the processing latency. So one typical example of this stream processing in LinkedIn, we have this call graph assembly. This is one typical stream processing task. What does it mean? In LinkedIn, if you click on the front end, then it triggers a request to the front-end servers, and then to render your page, there are multiple different pieces that need to be pulled from the backend, different backend data source as well. So in LinkedIn, we track that. When you click one, when user do a click on the front end, then it triggers a tree ID which identifies this particular request, and then the single front-end request translated into multiple back-end requests, it's carrying the same tree ID. So we have a way to track, okay, this is a call tree from a front-end user request to all the back-end. And all these servers in LinkedIn, when they receive a request, and they will log an event into Kafka saying, okay, this is what I saw as incoming request. But each different tiers of the servers will send out the service call request into Kafka in different Kafka topics. The request is now, okay, we want to understand from all those multiple tiers of servers, all the requests received from multiple tiers, how can we group them together, saying, okay, this is triggered by a single tree ID, and then this set is triggered by the other tree ID. So this requires the processing and the stream processing engine to sit in between, listen to all the incoming Kafka topics. Do it by repartitioning by the request tree IDs. And then in the Senza job, you need to identify, okay, the calls from the same tree IDs and assemble it into a call graph. So that is a typical use case of stream processing in LinkedIn. This is just give you one example of how the real-time stream processing use cases. So there are a few challenges that when you do this stream processing. First of all, then in order to process like hundreds of thousands of incoming requests, you need to scale up. And one strategy to scale is you need to have a partition in there. And second, as you can see in the call graph, when you start accumulating the request from a single tree ID, carrying the same tree ID, you need to keep some state in your process. So how do you manage the state? That's another tricky problem. The third is when your process dies and your data, you lost the data, and a lot of cases you want to reprocess from a certain position in the incoming traffic and say, okay, replay this data so that I can review my state. So how do you provide a mechanism to do that? Then what is the semantics you support in terms of failure? Do you do retain the store and how do you recover it, and how do you recover from the past process message? All those things is another big issue. And then the last one, well, not last one. The next challenge here is a lot of times you have the events description in the message. You receive it from the stream, but this only tells you a very concise amount of data about your user profiles or something like that. It only contains a user ID, for example. Now you need to join with a database with a database, or even the database may or may not be small. You need to join with the database to see, okay, with this member ID, what is the member's profile, and what is the member's like preference and those things. You need to decorate this data by joining the incoming request with a database, and that's a challenging point. Well, we will talk about it even later, that there's a request of joining two streams together to get data as well. The last one is, okay, you want to support, if you want to support a non-determinism result, you do some random switching. If you think about using this stream processing platform to do a large data, basically a data mining or machine learning algorithm, you want to reprocess data but apply a different random seed and try to see what is the consequence of that. You need some support for this non-determined when you replace all the messages. So those are all the issues or the challenges that you'll be facing when you're building a stream processing platform. Senza solves some of it, some important ones, not each and every one. So we'll get into the details of all those aspects. So now we're ready to talk about some key concepts in the Senza architecture. First of all, streams. So streams is both the input and output of a Senza process. Streams in Senza then needs to be partitioned, needs to be ordered within a partition, and it needs to be repeatable. Well, one practical example is Kafka. Since Senza was born sort of tightly integrated with Kafka concept, this is what Senza sees as a stream. So this is illustrating how a single stream with partition and ordering within the partition will look like. Each time you just append to, so for each of the partition, when a new message comes, it's appending. And that's the only operation, right operation you can do on each partition. When you read, then you can go back to any arbitrary offset as long as the partition is retained in Kafka.
So the targeting is based on the request ID or
yeah. So Kafka allows you to determine which is the partition key you want.
Just one, or can I use multiple?
You can use a composite key, but it has to be a. If you define a composite key, then you have to provide a way how you map the composite key to a hash key. So the second concept in Senza is called tasks. So what is task? Task is a logical computation unit. It's a chunk of code to process a stream. It consumes from one or more partitions from the input streams, and it may or may not send up to the output stream. So Senza also basically it pulls the batch of messages from all the input streams. We have an implementation of batch pulling from the Kafka consumers, and then this is purely for efficiency, for the performance. So this illustrates how, at a high level, what the task means. This one, a single task takes one partition as input, and this is basically the main interface that Senza expose and user needs to implement is called stream task. And that basically has one method. It's called process. Takes the input as an input message envelope, and then a message collector, which is the interface for you to send out the output messages. And then there's a task coordinator. This one is the one that allows you to maintain whether you want to commit a local state or not. So those are the basic basic interface and the three arguments. Think about it as a Turing machine that takes a taping. So each of these incoming message envelope represents a incoming event in the input tape of the Turing machine. And then this is output. Basically, this means, okay, when you have an internal state change and you want out something, that's the output tape of the Turing machine. The task coordinator now, you can think about it as internally you have a state change, and then the task coordinator allows you to choose when to persistent state. Okay. So this is a simple example showing how the implementation of a task would look like. This one, the task is pretty simple. We say, okay, we're consuming from the page view events, and then we just apply a counter per page key. So when we receive a message, we get the record of the message. We know from the record we get the message key, and then this in memory we just have a memory map of the counter per message key, and then you increment the counter and send the counter message out to the output collector. So concept is pretty simple. And there are more associated with in sense of the default implementation of a task. There's something rebuilding that allows you to do the to persistent state, and also to for you to go back in time and reprocess in case in terms when failure happens. So first of all, how does it do it? It periodically checkpoints the input streams with the offsets. So one typical failure case is, okay, you take one message, you say you consume the 10 message, you process it, and you send the output out, or you have updated your state, and at that time, your process died, and machine, say, power outage or whatever, the process crash. Now you restart the process, you don't know where to start from in that particular input stream anymore. So that's a typical problem that a lot of customers in LinkedIn before Senza, that when they write the code, they have to sort of write some local store or something that, by the spells to checkpoint those input streams. So Senza, based on that, and Senza has a building mechanism saying, okay, if you config a commit period, then Senza periodically will checkpoint each and every input stream's offset for you. So that way, if in between two commits and your process dies, it comes back, you can always go back to the previous checkpoint and restart. So you won't lose a state, and say your process is down for 4 hours, you will not lose data. Because Kafka only, if you don't have any offset to remember, Kafka only have 2 positions that you can use, earliest or latest. Right? So,
question here. So, where do you guys store or cache this? I mean, the data when you know the process crashed. So there must be a period of time of
so that's a good question. So there are 2 pieces of information that you want to persist, and we'll get to that implemented later. One is okay. So the question is, where do you store the data? Where do you store the internal Senza state and also the checkpoint when the process dies?
Also the incoming data.
Incoming data. Okay. The question to that, well, the answer to the last question, the incoming data we don't store. The incoming data you will have to replace from the Kafka stream.
So Kafka will be in charge of the.
Yes.
Okay.
Yes. And so for the next 2 questions, let me just quickly comment on that. Checkpoint and the local state, persistency of those 2 and how we recover that is all based on Kafka. We use Kafka as an archive and transaction logs to keep those states. The details will be covered later. Okay, thanks. And
just a question about if you have a lot of streams, right?
Mm-hmm.
Are you able to customize the different checkpoint rate for different streams?
Yes, we do. So the storage format we keep for the checkpoint is a map, a whole map of all the input partitions. For each partitions, where the offset is. So when you checkpoint, you checkpoint the whole map from the task. Okay. So that's the first thing, and I think with the periodic checkpoint, actually, the Senza task has one semantic failure guarantee, which is we provide at least once message delivery in this case. So the implication to that is duplicate messages is possible, but you will not lose it. Okay, so here comes the answer to the first question: where do we store the checkpoints? So as this picture illustrates, we save the checkpoint in the Kafka, in a separate Kafka stream as well. So in this case, message 1 and 2 from the partition 0 has been processed. Now it is time for the checkpoint, and the task itself will checkpoint the position of 2 in this Kafka topic. And the process continues with message 3, and it goes to the process, and then it has an output. But after that, the process dies. So in this case, when you recover from the failure, the task will read the checkpoint stream and get the latest checkpoint. since it was 2, so what happened is, okay, it assumes that 1 and 2 has been processed and it starts reading the messages in from 2 and resulting in a read process of messages. So that's how the checkpoint is associated with the at least once delivery semantics. Okay, so we've got through what I think next is to introduce another concept, key concept in Senza, which is the Senza jobs. So Senza job is essentially a collection of Senza tasks. And it can process more than one input stream, and then it provides, you can do filtering, reproduction, counting, etc., all those functions. One example of Senza job you can see from here is, okay, you have 2 Kafka topics, each have multiple partitions. One is at views, the other is at clicks. So you want to be able to join them and to see, okay, what is the impression versus like a click-through rate. Now, the whole job will have 3 tasks here, each processing a join for a particular partition in this example, and then the output is sent out to the output topic called add click-through rate with 2 partitions or arbitrary number. It doesn't necessarily match those 2, right? So the whole collection now is a concept of Senza job. This is illustrating basically when the message comes in, you will be able to join them together. So I'll skip that step. You can also use the different Senza jobs to connect together through different Kafka streams as well to build a more complex data flow workflow. In LinkedIn, we have the standardized and the feed processing teams already built this kind of complex workflow. You can see the first, in this example, then first level there you have 3 streams and then two jobs here. One is both doing a join. Job 1 is doing join between A and B. Job 2 is doing a join between B and C. And then they have different outputs, and those 2 outputs will be joined by the job 3, and finally you get another output. So this is an example of the data flows. Basically, you can see that the hierarchy is you have tasks, and then a collection of the same of the task is processing the same set of input and producing the same set of output becomes a job. And then you have different jobs which can be connected together with multiple levels of the different streams, which forms a data flow. So now we learned some of the basic concepts and in the Senza architecture. Now the question comes up, okay, how do you run it? How do you execute this Senza process in a distributed environment? When Senza was born, then the choice we made is, okay, we don't want to write our own distributed operating system or the distributed scheduling system to run the job. So we adopt Yarn from the Hadoop community to help us to run this job in a distributed environment. So why Yarn? Yarn offers a set of nice things. It does have a resource management. At that time, it was only memory, but I think right now it has memory and also CPU, C groups, isolation, and those nice features as well. And it provides, we said that. So it provides process isolation, actually, so the C groups, users, those features. And Yarn also provides a fault tolerance. In terms of a single container dies, then Yarn will detect it and relaunch the container at the same or different hosts based on the resource availability. So those are all nice features that Yarn already provides, and we don't want to rebuild, right? But there are a lot of since sensor born and for 1 year or 1.5 of the time that people start using it and adopt it, there is a strong need coming up saying, okay, we don't know how, especially from some industry that is not in this high tech, people will say, okay, we don't have expertise in Yarn, we don't know how to install and run Yarn. Can you provide us an out-of-the-box solution? Just say, okay, this is sensor standalone. I don't need to install anything else, and it just runs. So that is a fair request, and then we have already put energy in that. The sensor standalone will come soon. Okay, so in Yarn, how do we run this sensor job? As you recall, a single sensor job is composed of multiple tasks, and then it takes a set of input and you have a set of output. Now, there's a concept of a sensor container. This container is actually the container that we're going to ask the resource from them. A single sensor container basically can have one or two, is a collection of multiple tasks. So in this example, container one is executing task 1 and 2, and container 2 is executing task 3. This shows it. So, yeah, and this listed of some of the key features of the sensor container. So it breaks up the tasks into smaller containers and collection per container, and then execute one single Yarn container executes one or more tasks. One important thing is it's single threaded. So what does it mean? You have 2 tasks in a single container, but the whole container is a single threaded one. So every time you get a message that comes in, even if the message will be processed by 2 different tasks, it will go sequentially. It won't have a parallel model here. So the parallelism in Senza is per container. So if we want to scale out in terms of running more parallel things, then container is your unit to scale out. Please.
I ask a question that why do you receive a thread model in your container? Will there be some problem if you use your container?
Okay, so I'll first repeat the question. So the question is, okay, why we choose single-threaded model? Is there any drawbacks, right? So yes, the reason that we choose a single-threaded model are for at least for 2 big reasons. One, single-threaded model is to the programmer. The programming model is much simpler and easy. Second, in Senza, because in the whole we will talk about that later. So when you have a workflow that requires to commit a certain state, when you have to make sure that, okay, the process, for example, the state has to be committed after the output is sent. If you have to have these kind of guarantees, you will have to have a synchronized model of processing a single transaction. You will not be able to do it in a multi-threaded model saying, okay, I call send, and it's scheduled to another thread that comes back and immediately triggers my state commission, the persistent state. That won't work because when you call send and it's scheduled to another thread, you come back with the assumption you have saying, okay, the message has been sent, it's not true. So that's, hopefully that answers your question. Okay, second part, right, sorry, before I forget. Drawbacks, yes, there is drawbacks if you use this model, because now if your task is if a task is really I/O bounded, especially network I/O bounded, you call a RESTful point. In LinkedIn we have this model, we have this use case, and we recommend the user to like get some workaround for that. Because in this model, then you have a remote and network I will call, say, RESTful API. You call the REST, and then you're waiting here. Your CPU and all the message process, the pipeline is doing nothing, just waiting for the RESTful call to come back, and then you can continue. So this does create a performance bottleneck for the for this kind of a single thread model. One workaround that we actually I think we implement some of the LinkedIn engineers implemented is a batch model. So in this case, if you have a whole bunch of RESTful calls, you allow, say, up to 100. You don't checkpoint anything. You allow up to 100 messages comes in, and you make the RESTful calls. And on the 100th message, now you send out a RESTful call, you wait there. You wait all the hundreds to come back, and then you commit a state and move forward. So this is a workaround to address this performance downside in the single thread model. Basically, you batch, and then for each batch you do one.
Can you use the event model like you just?
Unfortunately, not yet. So I understand what you're trying to do is probably a single threaded, but you have a event-driven model. So each of the process will have different stages, and then you just go through that with the different stage. The current API doesn't support that. We'll have to think about more on that.
Okay, thank you.
Okay, so this the next few slides will talk about how Senza worked with Yang to start a job. So first step is we have a script to when we have a control script. When you say deploy Senza job, what it does is actually it goes to the Yang resource manager, submit the job, which the resource manager will spawn in application master. So when you have the application master, then the application master is in charge now. It talks to resource manager to get, okay, in a job, I need to schedule, say, I schedule 5 containers for 10 tasks. Each container contains 2 tasks. And the application master is going to negotiate with the resource manager to get 5 containers, and then when it gets allocated, it will talk to each and every node manager to say, okay, this is the Senza container, and with this configuration, you need please start and launch a Senza container. So this is the blue arrows is actually illustrating that model. So what if one of the container dies? So when the container dies, actually, that now the node manager and application master will be notified if the container dies. Then the application master will request for another, basically request for another host and node resource containers from Yang cluster. When it gets it, it will relaunch the Senza container.
Question here.
Okay.
Sorry, I just heard that you said when you because this is streaming processing, right?
Right.
But you're still using, like, say, the REST API. Basically, it's a wait and get a response and then move on, right?
Which part? The container part, or
yeah. My question here basically is, what if you have sent that request right into some RESTful API, and then this container dies?
Right.
Even though your application master has migrated this job to another host, right? But the REST API will respond to the previous one because he doesn't know that.
Well, when the container dies, and if you have a pending RESTful API's call, which what I would assume is there are 2 cases. One, the connection is immediately closed. Okay. In the case that the connection is the TCP connection is immediately closed, the RESTful server side will not really send any response because at that moment the request is aborted, right? Okay. Second, somehow the container is in hand state and the connection is still open. Yeah. So when that happens, if the connection is still open, the RESTful server will try to send the request back.
Yes.
But it won't get any response from this or acknowledgement from this container. So it will time out, right?
So when the new job has started, it will resend, basically will replay the previous message, right?
Yes.
And then your server side, it will just ignore it or something, right?
Okay, I see. So yeah, so if, first I will repeat the question. So the question is, okay, if you have a pending RESTful request on the server side, and then your container dies, you restart it, now the new container sends the same request to the RESTful server side, what happens, right? Okay, so in this case, if, say, your new and old containers have the same request and client ID, and your RESTful server side is recognizing any, is saying, okay, for any pending connection and the request ID and the client ID, I only allow one pending connection or one pending request. Then what happens is the new request will hang there until the old one gets timeout, right? But that's purely implementation details on the RESTful server side, right? So the RESTful server side can choose to say, okay, for any new connections, the context totally new, and I don't really block that, right? Okay. So now the question comes as, okay, I just realized this is a very popular Chinese blog statement. The question comes. Okay. All right. So this, when we talk about yarn and saying, okay, sensor uses yarn. Now, yarn is originally born saying, okay, it's for batch processing. So what's the difference? Why we, what's the difference when we use yarn to schedule a stream process, which is a long-running task, versus a batch process, right? So pretty much you can say, you can see from this whole stack comparison, one obvious difference is the persistent layer. Now it's no longer Hadoop, it becomes Kafka. And you can have, and above that, actually the APIs seems pretty magical. It's very similar to running a long-running batch job in Yarn, when you run Send on top of that. Okay. So next one, I think is getting more interesting to some of the folks here. In stream processing, if you don't really care about the state, just anything that you receive, you process. One typical example is filtering. You get the message. You look at all the fields and think, okay, this one either accept or drop. Then you don't really have any state associated with that. It's simple and easy. You don't, and your node crash. You start another place, no problem, right? The most interesting happens when you try to do this stream processing that is associated with some accumulated state when you have processed the history data, right? So this is showing progressively people will write a query like that. So this one is a filtering, say, okay, I don't need any state. Anything, if the column number value is greater than 20, yeah, accept it, right? So now it becomes more interesting when you say, okay, I need to, for all the values, I need to group by column 1 and do a count. Now you have some state associated with that. And then the next step is the query will be saying, okay, I have two streams, and now I need to do an inner join between the two streams based on the IDs. If the ID match, then I need to emit a state. So now you truly need some state machine between those two streams to be able to do the join. Last one, after join, you can do a order by and then do a limit, do the limit counting thing. So this will all require states. So two possible solutions available in the stream processing, in this distributed stream processing platform. One, you use a remote data store. This illustrates that. So okay, you keep all your state in a remote key value store, and all the tasks will read and write from the remote data store. And the problem with that is, okay, first of all, the RPC, remote RPC is really slow, and the typical incoming traffic for stream processing is roughly at 500,000 requests per second. But the database, the throughput is much, much less. The second problem is about the mutation. So when you have a remote data store, you say, okay, read, you get something, you put there. When you successfully call a put to the remote data store, there's no rollback. This mutation has been done, then you cannot really roll back. And this is one figure illustrated when we're using remote store, what happens. So in LinkedIn, we have a remote key value store called Baltimore. It is a key value store, and in the early days, some of our sender jobs were written by saying, okay, the state store is in Baltimore. So what happens is, okay, you can see normally it works fine, even like you accept the latency of the remote RPC call. It works fine until the point that, okay, there's the Kafka problem, then your input stream is going down, and then you need to do maintenance. Now you have a long accumulated input traffic waiting, and you restart the job. Immediately you see a surge of all the incoming requests to the Baltimore, and Baltimore will melt down in that case. So this is what the problem with the remote store will look like. So
I have a question. In this part, I don't think that would be the problem with the remote store. That would be the problem for a surge start. If you use some kind of a slow start, and that would be no problem, right?
well, that will mean you will have to basically in Senza now we cannot process the message as fast as possible. We need to throttle ourselves.
I mean that from this graph, it shows that the system can handle such surge. I mean that
No, so some of the containers just stop working at the point. So that's why the whole
I mean that
drops down.
for sustained traffic, it can handle. So if you use some kind of slow start, it can handle.
Yes, so that's a good point. So if the job itself try to throttle themselves to a certain amount,
Yeah.
right, then you can work with the remote slow store and gradually catching up. That's a good point. Okay. So based on, well, the problem about the remote store again is one thing that we cannot address is the slowness. Right? So if you have a remote store that you have to read and write, and the network latency is unavoidable. And later we will see another key feature that we want to have in the state management, which remote store won't give us, that will show here as well. So the choice we made to get around with this problem is instead of having a remote key value store, now we implement Senza state as a federation of local stores. So each task will have its local store, and in federation you have the whole key value store for the whole stream processing. So I guess the question here, the key question here is now, okay, you save your store locally, you have the fast access, and great, the throughput is also good. But what if the node dies? Where do you get back your local state, right? So the answer to that is now we attach a changelog stream for each of the local store here, and then this is in Kafka. So the concept is, okay, the changelog stream is our transaction log for each of the local stores. It is based by a distributed messaging system and distributed archiving, which is Kafka. So the assumption here is, okay, if Kafka loses data, then we're screwed. But as long as Kafka doesn't lose data, we have a transaction store. Then we have a transaction log we can recover from. So this illustrated as, okay, you have each mutation will become one message in the changelog stream, and now the task 3 dies. So when you restart the task 3, what it does is, okay, the Kubernetes store, the sensor internal implementation will go through all these changelogs here and restore to the latest state of the local store in the new task 3. So this way then you can always recover from any local node failures.
Who will do the checkpoint?
Pardon?
I mean that as time goes by, the size of the changelog will be larger and larger.
Yeah. So the question is, okay, this is ever growing. How do we maintain the size? Right? So Kafka, in Kafka, there's a feature for this log. It's called log compaction. What it does is, okay, for the same key, if you have multiple values in your log, you always compact into one, right? So in the sensor architecture, then we apply log compaction on this change log and periodically compacts the change logs.
So we're talking about database, right? I assume it's just pretty simple ones like key value stores, right?
Yeah.
Normal ones, so you can efficiently do those.
Right. Mm-hmm. Yeah, exactly. Sensors local stores are local key value stores. Yeah. Okay. So let's skip this. Oh, this, yeah, this, sorry. This is actually showing the log compaction. So these red ones are the repeat entries, and the log compaction is basically removing them so the size of the change log is maintained. Okay. Okay. So the current local store, the terms of key value local store, we support ROSDB for the persistent stores. The API is pretty simple, that we have put, get, delete, range. Recently we added a get all, which is leveraging the ROSDB's performance improvement in multi-get. And this illustrates the key value store's interface. So when you use the key value store, what you need to do is you need to implement a enable task which has the method of init. Then that is where you initialize your key value store. This hides a lot of things, but if you have any key value store that has a changelog attached, this init will automatically restore everything for you. Then when you get to the point you do the process, the state is already recovered automatically. User doesn't need to explicitly call it. Yeah, this is the illustration of how the stores are used. So,
I still have a question.
okay, yeah, please.
So in the join case, if the two streams are coming at different speed,
Right.
such as a curve and click, how can I join?
Right, so you will have to buffer it. So the question is, okay, in join, stream to stream join, especially, when the streams offsets are skewed, and then the keys that you're waiting to join is not immediately received from the other stream, how do you deal with the situation? So there's no really good answer to that question. I have to be very honest with you.
Okay.
But what we are building is now, what we're trying to do is to do a buffering in each of these streams. And then if your message is received within the buffer the time, then you will be having a meaningful join. If your display is so big that it's off the buffer size, then you will miss the join. Next is what we are we're still in dynamics and trying to implement that, is to follow the wheel-mill concept. So the wheel-mill has the model, mill will have the concept of processing late arrivals. So basically we're implementing a method also copying and cloning that behavior as well. That provides the capability for you to say, okay, if the join window, you miss the join window, but then you still have a late arrival coming from a certain stream, you can still process it, treat it as a late arrival. So that is exactly one of those window and join operators that we're working on.
But if you do buffering, it may block the stream.
No, not necessarily. You can always save in the killer store.
Okay.
Okay. So quick catch up on the coming up features. The current release is 09, and we are actively in the voting process to release the 09.1, and 010 is in the plan. New features include ROSDB TTL support. We added a coordinated stream and a standalone Senza, and then some high-level Kubernetes support. The ROSDB TTL support is basically there's a lot of use case in our Senza local store saying, okay, hey, I want to store all the incoming messages, but I only want to keep it for 2 days. Anything is earlier than 2 days, I want to delete. But so far, there's no very nice and clean purging mechanism in Senza that automatically helps you to clean away all this data that is older than 2 days. So with the ROSDB TTL support, we're adopting the ROSDB support for TTL, then that will be automatically purged, and user will never need to write a periodic purging task to try to purge and shorten the ROSDB stage. The coordinate stream is basically a method building to allow later even more advanced feature like the auto balance and auto scale and dynamic balancing. What it enables is there's the coordinate stream that every container and application master will listen to and publish message to. So it's sort of a control channel. Then the application master will be able to detect what is the ping, what is the hotspot and something, and dynamically change the configuration. So that's this coordinate stream is the foundation for the later changes like that. Standalone Senza, as I discussed in the beginning, this is mainly targeting for non-young users if they don't really want to run any sophisticated cluster management, and they will just adopt this standalone Senza and run it by itself. Yeah. High-level pure language and main thing we're working currently is the windowing operator and then the join operator. The target there is to build a physical operator library in Senza. Then on top of that, you can easily build a DSL language or a C language on top of that. Yeah. So that's what is the features coming soon, and this is the last page. So if you feel interested, contact us. The documentation side is there. The mailing list is here. We're welcome any contributors who are interested in the project.
I have 2 questions.
Sure.
Yeah. The first one is that how to do the repartition.
Repartition.
Yeah, and the second is that is it possible to increase the number of the workers along the manager is running?
Okay. So 2 questions. First, how do we do the repartition? Second is how do we increase the number of workers for the containers here?
Yeah.
Okay. So first question, repartition. Let me try to clarify with you. Are you talking about repartitioning dynamically? So when the job is running, you want to increase the number of containers.
Yes.
Okay. So that is not supported as well.
Okay.
So we actually, I just had a discussion with the Millwheel team member. Right now it's called Google Data, the data flow.
Yeah.
Eric Schmitz.
Yeah, actually.
Yeah. So we just had a brief discussion with him on the Hadoop Summit conference, and his answer is also okay. So if we want to do dynamic partitioning, Google Dataflow supports part of that. It also helps you to, if you don't really need to retain the state, it's an easy one. But if you need to retain the state, then the splitting of the state and the migration that will be a cost. But Google supports that. Google Dataflow currently supports that. So we are thinking about basically we need to study more about this model and see how the key thing is how do you share the state or migrate the state when you do the reduction. Yeah, we have not really had a plan to support that yet, but it's on the roadmap and discussion. Yeah. Second one, the number of containers. So the number of, if the partition doesn't change, then the increased number of containers is relatively easy. So as for Senza today, what you can do is just to change the container count and restart job, it will automatically scale out. The next feature that we are implementing is to be able to to be able to increase the number of containers without start and stop the job. So that is the work that is in design right now.
So for the change logs, they're keyed by the partition number or by the container number?
The change log is keyed by the task. So as long and the task is basically almost one you can consider one to magnitude partitions. So that said, the change log, is per partition as you.
So two real workers may process the logs from the same partition. So maybe.
No, that won't happen. So. Yeah, so the assignment, the partition assignment logic guarantees there's no two workers working on the same partition. Yeah.
Among those features, what are the ones that make, three questions. The first one, among those features, what are the ones that make Senza near real-time performance? The second one is, there was a slide about a SQL-like language. Does that mean Senza also expose an interface for SQL-like language? The third one is, my understanding for Senza is that's a frame architecture for stream processing, but does Senza provide some components to process like filter, message enricher?
Okay. Got it. So let me first repeat the three questions. So the first question is, sorry.
What makes the performance of the user performance?
So what are the choices that what are the choices we make to achieve high performance in Senza? Second, when we say high level language support, what does it mean? What does it mean? Is that the APIs is a SQL parser or SQL console, or what does it mean? And then does Google Senza also provide a certain library for people to do have a set of building processors people can pick and choose, just drop in, right? Okay, so let me try to answer the question 2 and 3 first, because those two are connected. So first of all, what is interface? Front-end interface to data scientists who are writing these SQL queries. We do not have a decisive answer yet. What we are trying to do is, if you look at the whole space of saying, okay, this is the front end, you write some query, and then you push down to the execute engine, and then you do it. So there are multiple levels. One is, okay, the front end user interface, how the user will write the query, and second, you need to pass it, and you translate it into a format that the backend execute engine will recognize and pull in, and then push down to the deployment, right, and then run it out. So what we're trying to do is to do a bottom-up approach. So first of all, we want to build up basically a set of fundamental physical operators in the and works like a library, and then on top of that, now you can build an intermediate representation layer that is basically how you execute, how you use those operators to connect together for a certain period and then execute it, right? Now, that upper level, which is the SQL console, it stands as a front end. So this is the topmost layer that basically what we are trying out is to adopt this something like a stream, it's called a SQL stream. We adopt some SQL stream syntax and semantics. So what you have is a SQL stream front end. You write this SQL query, and then we have a query parser and planner to translate that into the intermediate execution plan for Senza, and which is composed of all those physical operators, and then you can push down to the Senza execution engine to execute this query. So to answer to after setting up all those contexts, the answer to your question is first of all, do we have a pre-built set of processors? Yes, it will be in the plan. We'll have a set of preset physical operators as a library for the user to become the use. Second, what is the front end of the SQL engine? So that, in my opinion, it will be something like a web interface that you can type in the SQL statement, and then the web portal will be the one who pass it, generate a query execution engine, and send back to our backend. Right? So that will be the ideal layered and front end API for the end users. So your first question. Sorry, remind me again. What was that? Oh, the performance, right. So the key performance choice that Senza made to basically allow this high throughput, I believe, are twofold. One is the persistent layer. Now we use Kafka as the persistent layer for all these append-only logging systems. Second is the local store choice. So the local store choice basically avoid all those network I/O bounded operations that we will be potentially facing. That doesn't really completely cover all these possible performance issues, like the friend at the back was talking about. Okay, what if you make a RESTful call? That is still a pain point. But in the basically in the near term, then we are trying to do, for example, a lot of use cases for this RESTful call is because you have some adjunct data that you try to decorate your event with. So we are one approach, and then this set of adjunct data is usually static. You don't really change it often. So what we are exploring too is to have a way to bootstrap with part of the adjunct data locally. Then you don't need to make those RESTful calls. Hopefully I answered that.
Thank you for sharing all the information. I have a question related to the open source ecosystem, for example. I want to know beside LinkedIn, who is the main contributor, and then in the whole process, what is the most benefit you get from this open source community to LinkedIn?
Okay, so first of all, the outside LinkedIn, who is using Senza? Who is developing and who is using Senza? So we have, Senza is a relatively still young project, so I think so far we have about dozens of outside company users. The big one, of course, LinkedIn, and then Netflix, and then a TiVo company. I forgot it's not a TiVo company, it's not TiVo the company, it's a subsidiary of the TiVo company who's using that. And then there's a MetaMarket, and a few others. So there's I would say the community is growing and is still is quite vivid. So the second question is about.
What is the benefit of
Oh, okay. So for LinkedIn, so this one hard to say. Any open source project actually has always, if you look at that, that's my personal opinion. It doesn't really represent LinkedIn. So any open source project, it will become popular if outside company like LinkedIn, if it address some pain points in the platform like the utility side, right? For example, Kafka is a great example because Kafka it has a simple API, a set of API. It solves a lot of the message delivery problem, the pub system problem in the large delivery system. So these two, a lot of adopters are mid-sized or small companies. They don't have any to invest into this utility. So that's why the open source community, as long as you have a basic function setup for this utility functions, then the adoption is fast, and then there are a lot of contributors come. Right? But for LinkedIn, what is the benefit? I think the LinkedIn benefit is, okay, the branding, technical branding is of course the one big thing for LinkedIn. And then the real, of course, we have some, in that case, if there are a lot of outside committers, we get a lot of free labors in a sense as well, right? So that's all the basic concept of open source. But in my opinion, then some of these, like in a certain stage of the open source project, often the need from a big company versus the open source community, which is 80% is a mid-sized or small company, the interest will diverge. So, for example, there's no one in open source ask for, okay, running this as a multi-tenant service, or running this as like large platform, like I open up for all the customers to come in. But in LinkedIn, or in large companies, other large companies like Netflix, it is a need because internally you need to be able to build a system that supports multi-tenancy, and you have different teams with different projects come on board. You need to be able to manage the resource and then isolate their usage, or even sometimes like doing the order management, the service allocation, and supporting a self-service portal. Because the team inside within the company with thousands of customers, hundreds of customers internally, you only have like say a team of 10 people. Even that's extreme. Like you have a 10 dev to support that. It won't be possible if you don't have a self-service and run a software service platform and the infrastructure set up for that. Just the case that the other day you're reviewing all those onboard requests, it will kill you. You will not be able to write a single line of code if you're doing that manually every day.
Yeah, this is a very generic question. I think a lot of people are asking on the internet. So how are you going to? Thank you. So how are you going to compare this Samza, Spark streaming, and so on?
Yeah, popular questions. So, stream platform right now you have choices on Storm, Spark, and then Zen. So it's interesting. All start with the S, I guess, because streaming is really the word. Okay, so the comparison between them, there's a long list of basically feature comparison on our Twikibate, on our Wikibate as well. So compare with Spark, compare with Storm. There's a detailed, nice write-up of like dozens of pages of that. But just to shorten it, and in my personal view, there's this comparison. So Storm and Samza is all controlling the incoming, processing the incoming event in the granularity of a per event base. And Storm has a core state management system, it won't really allow you to have a large state manual. But Storm has a nicer API, which is Trident, the sort of like a DSLI programming API. And then Storm currently provides a workflow management, which Sensor doesn't. So that's between them. And the more interesting is Spark. Okay, how do you compare Spark with Sensor? So first of all, Spark is a micro batch based system. So the granularity of if you talk about the granularity of this system, like how can I say, processing unit, it is not single event. So it is a batch-based system. So you can tune the batch size so that it mimics the events in streams coming. What's the significance of that? I may not care whether I process per event or per batch, right? So the problem here is more subtle. I talked with the Spark guys as well. One question I was, because I'm building it, I asked is, okay, Spark streaming, you can do the window aggregation, you can do all this window-based operation, then what happens if the window is going across the batch boundaries? And the answer is no, it's not supported. So this is a limitation that if you have granularity of the processing unit down to the per event, you won't have this problem. But if you have a batch system, you will have this problem. So that's first. Second is the persistent layer. The difference in the persistent layer, if you compare Storm, Spark, and Sensor, is quite different. So Sensor is a purely stream-based system. So its persistent layer is Kafka, which and then Spark and the Storm is based on HDFS for the persistent layer. What does it mean? Again, I would say the performance. So what happens is recently Spark also has an improvement. So for the state management. Spark basically, the Spark 1.3 added the failure recovery mechanism so that you can, if you have a state, say in the RDD format, and then you want to persist it, you can also persist it through the file system, and they call it fault-tolerant file system, right? So I didn't really read any detailed specification of what this fault-tolerant file system is, but the implication is HDFS. So the problem with that is, okay, if your state is really large and the nature of this like storage, this persistent storage is append only, and you read back when you read back into the memory in Spark mode, right? You read back into memory or read back into the local node, then more performant way is to have a transaction log. Which is, you should use a distributed logging system like the Kafka instead of putting it into another file system. So that's my personal opinion. The big two things is granularity of the processing unit, and then the underlying persistent storage support. Okay. Any more questions? Well, I think I ran over time, so thank you for everybody.